Okay, so in chapter 5, since we've learned in chapters 3 and 4 how to make our compounds, we now need to start looking at how chemicals actually react with one another and in making measurements for those reactions. So chapter 5 is going to deal with the classification and balancing of chemical reactions. So we'll learn how to write our chemical equations, and then we'll teach you how to balance those chemical equations. Then we'll talk about classes of our chemical reactions, and that will actually take up most of the rest of the chapter. So looking at precipitation reactions, acid-base neutralization reactions, our redox reactions, how to recognize each of these different types of reactions, and then this process of writing net ionic equations will be the last step for chapter 5. So those are going to be our major goals. How are our chemical reactions written? How chemical reactions of ionic compounds are going to be classified? What are oxidation numbers and how are they used? And what is a net ionic equation? So you should be able to answer all of these different questions by the end of chapter 5. So chemical reactions can be thought of as recipes, and that's typically how chemists will actually work, and a lot of science actually works that way. You go into the laboratory and you add a little bit of this to a little bit of that, and you see what happens. So it's a lot like cooking. So you have starting materials that are called reactants, or sometimes they're called substrates, and then you mix these together and you end up getting products out on the other side. So we started, when we were talking about chemical reactions, listing these with their chemical names. So now we're going to replace those chemical names with their chemical formulas. So a chemical equation is going to be an expression in which our symbols and formulas are going to be used to represent our chemical reaction. And so this is essentially the language of chemistry. So in this equation, we've got the reactants or substrates on the left-hand side of the equation. So that's what we're putting into our equation. If you recognize this one's the sodium bicarbonate, and it has a common name. Do you remember that common name? This is baking soda. So in this equation, if we take baking soda and we heat it, it actually will break apart, and it will form sodium carbonate. You'll notice the hydrogen is now missing from this one. Hydrogen has actually come out, and it's come out in the form of water, and carbon dioxide has also come out in this breakdown process. So the reactant is going to be the substance that undergoes the change in the chemical reaction. So we're starting with this. It's our starting material. And then the products are going to be the thing that we end with. In this case, there are 3 components that our product is going to encompass, and that's because our reactant is going to break down into these 3 different components. So if there's anything that needs to be added to make the process happen, that's usually indicated above the arrow of the reaction. So in this case, the sodium bicarbonate won't break down into these 3 products unless it is heated. So heat is required for this reaction to move in this direction. So within our chemical equations, we have to observe a specific law, and this is the law of conservation of mass. And so this states that matter cannot be created or destroyed in a chemical reaction. So all of the atoms that we start with in the reactant side of the equation have to be represented on the product side of the equation. They can't disappear. And we can't add extra things in there as well. If there's something that happens on the left side of the equation, it has to be represented in the same atomic masses and same atomic elements that are represented on that reactant side. So the only things that change are going to be the bonds between the atoms. So these can change from the reactant side to the product side. So reactants can be rearranged to form new compounds, but none of the atoms are going to disappear and no new ones are going to jump into our equation. So we say that our chemical equations then have to be balanced for both the numbers and the kinds of atoms that are used within our reaction. They have to be the same on both sides of the arrow. So we represent then the number of atoms that are, or molecules that are going to be placed within a reaction using a coefficient. So the coefficients multiply all of the atoms in the formula. So you have to be sure to consider the coefficients when you're deliberating if you have a balanced equation or not. So we'll see many examples of this, and I'll point out the coefficients as soon as we get back to another equation. So substances then that take part in our chemical reactions can be in any of the three phases. So they can be in the form of a solid, a liquid, a gas, or they can be dissolved in usually water. So this information is also added to our equation, and so you'll see these by placing the symbols after the formulas, and the symbols are always in parentheses. So if the compound is in the form of a solid, after you list the compound, like sodium chloride for example, you would put these parentheses and the small s in there, and that would indicate that it's in the solid state. So you got solid, liquid, gas, and then this is dissolved in an aqueous solution, which means that the compound is dissolved in water. So aqueous means water. So AQ. So that's different from being in the liquid state. Remember, if we have liquid sodium chloride, that means that we've melted the solid by heating it or putting it under extreme pressure to get it to go into the liquid state. If we take our solid sodium chloride and we drop it in a glass of water, the sodium and the chlorine will separate from each other into their ionic forms, and this represents an aqueous solution, or the dissolved state. So it's different from the liquid state. So when we're writing our balanced equations, we're going to have certain steps that we need to follow to actually balance them. So we'll go through these steps, and then I'll also do a video tutorial with you guys so that you guys can do some practice in balancing chemical equations. So step one, you're going to write an unbalanced equation, and you're going to use the correct formulas for all of the reactants and products. So the first thing that you need to do is write the correct molecular formulas for the different compounds that are involved in your reaction. So for example, anytime we have hydrogen and oxygen, they have to be written as H2 gas or O2 gas rather than just simply H and O, because they don't exist that way in nature. They exist as the diatomic molecule, so you always have to show them that way. So we also have subscripts then in the chemical formulas cannot be changed, because if you do this, you would change the identity of the substance in the reaction. So anytime you're representing oxygen gas, it has to be O2. You can't change the subscript to get more oxygen in your reaction. So step 2 involves adding appropriate coefficients to balance the number of atoms of each element on each side of the equation. So typically to do this, you want to begin with the elements that appear only in one compound or formula on each side of the equation, and then leave the elements that exist in elemental forms like oxygen and hydrogen until the last thing that you do. And that typically will make it easier to balance. So here's an example of an equation. We've got sulfuric acid plus sodium hydroxide, and it is yielding a salt and water. So you've got sodium sulfate and our water molecule on the product side. So what you'll notice if we go through and we look at the number of atoms on each side, let's start with numbers of sulfur or sulfate. So in this, we're looking at this molecule. These guys are ionic. We know that sulfate is an anion. It's a polyatomic anion. So when we're looking at chemical equations, these typically will move together as an ion. So we can see that on both sides. So we've got one SO4 over here, and we've got one SO4 over here. That's actually balanced. Let's take a look at sodium. We've got one sodium over here, and we've got two sodiums over here. So this is not balanced. We need another sodium on this side to balance the two sodiums that are on this side. So to do this, we can't change the subscript because that would change our molecular formula. And then we would have an incorrect number of sodiums that are actually bonded to the hydroxide ion. So to increase the amount of sodium on this side, we have to add a coefficient. So we add this coefficient in front of this molecule, and what that says is that there are 2 complete sodium hydroxide molecules. So we've got 2 sodiums extra, and we've got 2 hydroxides extra. So the sodium's now balanced. Now let's take a look at the OH. So when we are drawing our molecule of water, sometimes you can think of it as HOH when you're thinking of that molecule coming together, where one of those H's is going to be the cation and the OH is going to be the hydroxide anion. So remember we said acids and bases, water can act as an acid or a base because it can get rid of a hydrogen and it can also donate that OH portion. So in this case, we've got 2 hydrogens here, and we also have a hydrogen over here, right? So there's, well, if we actually place 2 here, so we've got 2 here, and we've got 2 here. So we've got a total of 4 hydrogens on this side. If we look over here, this is still not balanced for the hydrogen because we got 4 on this side, but we only have 2 on this side. If we look at the number of oxygens coming from the OH anion here, we've got 2 oxygens here, but we only have 1 here. We don't count the 4 that are in the sulfate because they're already accounted for by that sulfate anion. Those 2 guys balance, so we don't need to worry about them again. But we need to get 2 oxygens and 4 hydrogens on this side, so we can add a coefficient of 2 in front of the water to balance it for the water molecules as well. So we have our 4 H's and our 2 oxygens over here. And so if we place this coefficient of 2 then in front, we're going to balance our equation. So this represents the completely balanced equation. So it has the same number of atoms of each type of element on this side of the equation as it does on this side of the equation. So step 3 in writing your balanced chemical equations is check the equation to make sure the numbers and kinds of atoms on both sides of the equation are the same. So we just went through that step in the last equation. And now step 4, you have to make sure that the coefficients are reduced to their lowest whole number values so that you get a reduced equation. So that is the case here. We can't reduce this any further. It's as low as it can be to get the lowest amount. We wouldn't say 4 and 4 here, for example. It could reduce to 2 and 2. So in summary of balancing our chemical equations, the polyatomic ions that appear on both sides of an equation can be treated as a single unit. They're going to move together. So if you've got hydroxide or sulfate or ammonium, these are all going to move as a complete distinct unit. So that's one hint. Move your polyatomic ions as units. And then you're going to make sure that your molecular formulas are going to be correctly drawn on both sides of the equation. And then you can balance the elements in the most complex molecule in the chemical equation first. Leave the hydrogen and oxygen containing compounds or water containing compounds for the last thing that you're going to balance. If an equation contains your pure element as a product or reactant, then assign that element's coefficient last and leave oxygen and hydrogen either for the last or near the end of the balancing steps. So these are just the extra hints that'll help you balance chemical equations correctly. So now go ahead and take a look at the review of some practice balancing chemical equations.